Solve the polynomial inequality and graph the solution set on a real number line. Express the solution set in interval notation. The inequality we're working with is x squared less than or equal to 8x minus 13. So we're going to start off by rewriting the inequality with 0 on one side. So if we move all the terms to the same side, we'll have x squared minus 8x plus 13 is less than or equal to 0. Then we need to identify what the boundary points are, and we're going to find the boundary points by solving the equation x squared minus 8x plus 13 equals 0. So I'll try to factor this. Let's see if the factors of 13 and 1 don't add up to be the middle term with an 8, so it doesn't look like we're going to be able to factor. So instead, I'll solve using the quadratic formula. So A is equal to 1, B is equal to negative 8, and C is equal to 13. And the quadratic formula is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So I'll substitute a, b, and c into the formula, and that'll give negative b plus or minus the square root of negative 8 squared minus 4 times 1 times 13 all over 2 times 1. I'll start to simplify this. The double negative will become positive, so we have a positive 8 plus or minus the square root of 64 minus, I need to know what 13 times 4 is, that's going to be 52 over 2. And we have 8 plus or minus the square root of 16 minus 52, 64 minus 52, and that would be 12. And let's see, I can simplify underneath the radical. 12 is 4 times 3, and I'll continue up here. The square root of 4 is 2, so I have 2 square root of 3 over 2, and we can divide that 2 into both of those terms to get 4 plus or minus square root of 3. So our boundary points are going to be 4 plus square root of 3 and 4 minus square root of 3. So I'm going to mark this on the number line. And 4 minus square root of 3 will be less than 4 plus square root of 3. I'm going to go ahead and mark my boundary points with filled in dots because my inequality has an equal to in it, so I know these boundary points will be included in the solution set. That's 4 minus square root of 3 and 4 plus square root of 3. And we need to test each one of these intervals to determine whether it's a solution to this inequality with less than or equal to 0. So I'm going to test points into the expression x squared minus 8x plus 13 to see whether they come out positive or negative. So to figure out what my test points are going to be, I want to figure out what 4 minus square root of 3 is. So let me grab my calculator. And it's going to take a moment to load. And while it loads, I can go ahead and test in between these two. Let's see. So the number 4 should be in between 4 minus square root of 3 and 4 plus square root of 3. So I can go ahead and test that point. And I'm testing it in the expression x squared minus 8x plus 13. Okay, my calculator loaded. So 4 minus square root of 3 is going to equal 2.3, and 4 plus square root of 3 is 5.7, so 2.2 and 5.7. That's going to help me identify my test points. So as I said, I'm going to test 4 into this expression, x squared, that's 4 squared minus 8 times 4 plus 13, and that works out to be 16 minus 32 plus 13. 16 minus 32 is a negative 16 plus 13, and that will equal negative 3. So my test point came out negative in this interval. So then I'll use 0 as a test point in this interval on the left. So if I test 0 into x squared minus 8x plus 13, that's 0 squared minus 8 times 0 plus 13, and that works out to be 13. So my test point came out positive in that interval. And then finally, let's test, say, 6. And we have 6 squared minus 8 times 6 plus 13. 6 squared is 36. 8 times 6 would be 48. 36 minus 48, that is negative 12. And negative 12 plus 13 is a positive 1, so we get positive in this interval. Now the inequality that we have is less than or equal to 0. Negatives are less than or equal to 0, so we're going to use this middle interval as our solution set. So in interval notation, I'm going to use brackets to include the boundaries. And our interval starts at 4 minus square root of 3 and ends at 4 plus square root of 3. Determine whether the following function is a polynomial function. If the function is a polynomial function, state its degree. If it's not, tell why not. Write the polynomial in standard form, then identify the leading term and the constant term. The function that we're working with on this example is f of x equals 4x plus x squared. And we want to know whether this function is a polynomial function. So I've put the definition of a polynomial function down here. A polynomial function is going to be of the form f of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus, and so on until we get to this end of the pattern, a sub 2x squared plus a sub 1x plus a sub 0 or a naught. When n is a non-negative integer, so remember n is the exponent on here, so n is a non-negative integer such as 0, 1, 2, and so on. So this part of the definition is describing that this exponent It has to be from this group of numbers, the non-negative integers. And the rest of these exponents will be as well, because you can see that if n is a non-negative integer, n minus 1 will also be a non-negative integer. And we do have a stopping point for these exponents. We stop at an exponent of 0 here. We also need the coefficients a sub n minus 1, a sub 2, a sub 1, and a naught to be real numbers. So the coefficients are these numbers that are attached to the variable. So looking at our example, we need to focus on those two parts of the definition. We need the exponents to be non-negative integers, and we also need the coefficients to be real numbers. So we have x, this x has an exponent of 1, which is a non-negative integer. Then we have x squared, that's also a non-negative integer, so it fits the first part of the definition. The coefficient here is a 4, that's a real number, and the coefficient here is a 1, and that's a real number. So f of x is a polynomial function. Now we want to state the degree. The degree of that polynomial function is this highest power on the variable. So for our example, n will be 2 because that is that highest power on x. So n is 2, the degree is 2. And for us to write this polynomial in standard form, the adjustment that we're going to make is to write it in descending order so that the highest power is first. So that would be f of x equals x squared plus 4x. The leading term is x squared. And the constant term would be the last term, and that term does not have a variable. And our constant term is going to be 0. We don't have a term listed here without a variable, so we're going to assume that is a 0. Determine whether the following function is a polynomial function. If the function is a polynomial function, state its degree. If it's not, tell why not. Write the polynomial in standard form, then identify the leading term and the constant term. We have g of x equals x to the 7/2 minus x to the 4th plus 5. I've written down here the definition of a polynomial function, and a polynomial function is of the form f of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus ... that means and so on, meaning that the pattern continues. And the pattern that we're supposed to be looking at is that we had a power of n on the first term, and the next term has a power of n minus 1, so 1 less than the one before. And we continue that pattern until we get down to a power of 2, then a power of 1, and then no variable, which is a power of 0. So the key thing that we want to pay attention to is that n, that power on our x, needs to be a non-negative integer, which is 0, 1, 2, 3. So the powers are restricted to being these values right here. The powers on our variable x is restricted to these numbers. And looking back at our function that was given to us, remember we want to determine if this is a polynomial function. You can see that the power on x is 7/2, which is not on our list of values. So we can say that this is not a polynomial function. And because it's not a polynomial, we are not able to identify the degree and the leading coefficients and these other requests. For the polynomial function below, we want to list each real zero, its multiplicity, determine whether the graph crosses or touches the x-axis at that x-intercept, determine the maximum number of turning points, determine the end behavior, and that is to find the power function that the graph of f resembles for large values of absolute value of x. So we're looking at this polynomial function f of x equals x minus 5 cubed plus x plus 6 squared. Now, luckily, it's already in factored form. So we can list out the factors here as x minus 5 and x plus 6. And if we set these factors equal to 0 and solve, we're going to get the real zeros, or the x-intercepts, of this polynomial function. So by setting x minus 5 equal to 0 and solving, we would add 5 to both sides and get x equals 5. So we have a real 0 or an x-intercept at x equals 5. We'll do the same thing with the other factor of x plus 6. We set it equal to 0, solve by subtracting 6 on both sides, and we get that this polynomial function has a real 0 or x-intercept at negative 6. And then we want to decide what the multiplicity is. Now the multiplicity is going to be how many of that factor we have. So for the factor of x minus 5, we have 3 factors of x minus 5. So that tells us that this 0 has a multiplicity of 3. And the factor of x plus 6 has a squared on it, so we have 2 factors of x plus 6. And this 0 has a multiplicity of 2. Now the multiplicity is what determines whether the graph will touch the x-axis at that 0 or cross the x-axis at that 0. So because this multiplicity is odd, the graph will cross the x-axis at x equals 5. And because this multiplicity is even, the graph will touch at x equals negative 6. So going back to my instructions, we've listed each real 0 and its multiplicity. We've determined whether it crosses or touches. We want to determine the maximum number of turning points, the end behavior, and find that power function. So I've got one more table here that we're going to work with. And we want to know the degree of that polynomial. The degree will help us determine the maximum number of turning points. So the degree will be the sum of these two powers. These are powers that are on x. So if we were to multiply this out, the highest power on x would be x to the 5th power. So when it's in this factored form, the shortcut is that we can add the powers on the variables. So we've got a degree of 5 for this polynomial. And when we have a degree of 5, that means the maximum number of turning points will be 4, one less than the degree. The leading coefficient will help us determine the end behavior. And the leading coefficient will be a 1 in this example. We have a 1 as the coefficient on x, and on x here, and there's no coefficient out here, so 1 times 1 will give us a leading coefficient of 1. So that's going to help us determine the end behavior, or the power function. So the power function will be x to the 5th power. And when we have an odd degree with a positive leading coefficient, that means our end behavior is going to go in opposite directions, and it's going to be negative on the left and positive on the right. So our power function is x to the fifth, and our end behavior is that these ends go in opposite directions, down on the left and up on the right. On this question, we want to determine whether the graph on the right could be the graph of a polynomial function. If it could be, we want to list the real zeros and state the least degree the polynomial can have. So in order to determine whether this graph could be the graph of a polynomial, we need to know what the graph of a polynomial looks like. The graph of a polynomial function is both smooth and continuous. Smooth means that the graph will contain no sharp corners or cusps. And continuous means that the graph has no gaps or holes and can be drawn without lifting your pen from the paper. So looking at the second part that says continuous means that it has no gaps or holes, we can see that this graph has a gap in it. We can draw this portion without picking our pen up. However, we would need to pick up our pen to jump to this section. So there is a gap in the graph. It is not continuous. So this graph cannot be the graph of a polynomial because it's not continuous. This is not a polynomial. Thank you for checking out my videos. Have a great day.